Today, we are diving into the CPU's own treasure map, a guide to what we call addressing modes. So, have you ever really stopped to think about this? How does your computer actually find one single piece of data in like a sea of billions of them? Every single click, every key you press, the CPU has to go find the right information. But with so many places to look, how on earth does it pinpoint the exact spot? Okay, to make sense of all this, let's think of it like a treasure hunt, right? The CPU, that's our treasure hunter. The instruction it gets from a program, that's the treasure map. And the data it's looking for, well, that's the treasure itself. So these addressing modes we're talking about, they're just the different kinds of clues on that map. Simple as that. So let's start with the easiest clues imaginable, the kind of clues where the treasure is basically just drawn right there on the map itself. This first one is called immediate addressing. And it's so simple because the treasure, it isn't even buried. It's right there, literally part of the map's instructions. The data the CPU needs is included directly in the command it receives. Okay, so for example, look at a bit of code like add EAX, 5. All this is telling the CPU is, hey, add a number to this specific spot. And what's the number? It's 5. It's right there in the instruction. The CPU doesn't have to go searching for it anywhere else. Now, this is where it gets interesting, because there's always a trade-off, right? The big advantage here is speed. I mean, it is blazing fast, because you don't need to make any extra trips to memory. But the limitation is pretty obvious. The data has to be small enough to physically fit inside the instruction itself. Okay, so what if the treasure isn't on the map? Well, our next clue is called direct addressing. Now, this is more like a classic treasure map. The instruction doesn't have the treasure, but it gives you the exact X marks the spot location where it's buried. Yeah, the formula for this is about as simple as it gets. The effective address, where the data actually is just the address that's written right in the instruction. It's like the map is giving you the exact GPS coordinates. You just go to that spot and boom, there's your treasure. And again, here comes the trade-off. It's pretty efficient, right? You only need to make one trip out to memory to grab the data, but you're limited by the map. If your world, your memory, is huge, you're going to need a lot of space in that instruction just to write down the full address. Okay, so a key thing to remember is that going out to main memory, that's slow. It takes time. So what if our treasure hunter had like a little high-speed notebook to keep the most important clues right in his pocket? Well, that's exactly what registers are. This brings us to register addressing. With this, the instruction doesn't point to that slow main memory at all. Nope, it points to a register, which is a tiny, super fast little bit of memory built right inside the CPU chip itself. The data's already there, ready to go. It's just unbelievably efficient. Just to give you an idea of how efficient, in a standard x86 processor, you only need 3 little bits in an instruction to point to one of 8 different registers. 3 bits! That's nothing. It makes the instructions incredibly compact. And that incredible efficiency leads to the main takeaway here. This is the absolute fastest way to get data. Full stop. The instructions are tiny, and there's no slow trip to memory. The catch? Of course there's a catch. The CPU only has a handful of these registers. It's like prime real estate, very valuable and very limited. Okay, so what if we start combining these ideas? This is where it gets clever. With register indirect addressing, the clue on our map says, hey, look in your high-speed notebook. That's the register. But when you look in the notebook, you don't find the treasure itself. You find the address of the treasure, which is still buried out in main memory. And this is such a brilliant way to see the performance boost. Normally, if you had to look up an address in memory to find another address, that's 2 slow trips to main memory. One to get the address, the second to get the data. But by putting that first address in a super fast register, we completely eliminate one of those slow trips. It's a huge win. All right, so we've seen the basic clues. Now let's get a little more advanced. Let's look at clues that require our treasure hunter to do a bit of math to figure out the path. This brings us to displacement addressing, and this one is one of the most powerful and widely used modes out there. The idea is that the map gives you 2 things, a starting point, which you get from a register, and an offset, or a displacement, that you add to that starting point. And our treasure map analogy just makes this crystal clear, right? The clue isn't some set of GPS coordinates. It's more like start at the old oak tree, that's your base address, and then walk 20 paces north, that's your displacement. This combination gives you a ton of flexibility.
And a perfect example of where this is used all the time is something called indexed addressing. This is absolutely essential for working with arrays, lists of data. The base address points you to the very beginning of the list, and then the other value acts like an index, letting you pick out exactly which item you want.
So let's walk through it. The CPU does the math to find the address of the first item. It goes and grabs the data. Now, to get the next item in the list, it just has to add 1 to the index and do it again. It's this simple, repeatable loop that makes it so ridiculously efficient for crunching through huge lists of data.
Okay, so we've looked at all these different types of clues one by one. But how does a real modern processor actually put this all together in its toolkit?
Well, just take a look at this. This really shows you the sheer variety that a modern CPU needs to have. Something like a Pentium processor doesn't just use 1 or 2 of these. It mixes and matches all the simple ideas we've talked about into this huge, powerful toolkit with a dozen different ways to find data. And all that variety gives programmers and compilers the flexibility they need to write the absolute most efficient code possible for any task. And all of this really leads to the central challenge, for anyone designing a CPU or writing a program. Which clue, which map, is the right one for the job at hand? At the end of the day, this is the core lesson. It's all a balancing act. You've got modes like immediate and register. They're incredibly simple and fast, but they're not very flexible. Then you have something like displacement, which is super flexible and powerful, but it means you have longer instructions and the CPU has to do more work. Choosing the right mode has a direct impact on how big your program is and how fast it runs.
And so that kind of leaves us with one final big question to chew on. These addressing modes, they've been the absolute bedrock of how computers work for decades. But as we start moving into totally new worlds like AI and quantum computing, what kind of new, completely different clues will future processors need? What will their treasure maps look like?